Hello, my name's Guy Davidson, and it's great to be back. Last time I was here, I spoke for quite a long time. Who was here last time? And you came back. Great. Lock the doors. For those of you who weren't here, last time I came here, I basically gave my introduction to computer science talk, and it goes on for about 4 hours, and I usually deliver it over a number of days. But the audience said, no, keep going, keep going. I was like, all right then, I'll keep going. Great, yeah. 3 hours and 40 minutes later, somewhat dehydrated, I completed the talk. This is a rather simpler talk. Abstraction, the true superpower of C++. Lots of people talk about, the true superpower of C++ is blah, blah. It's abstraction. And I'm going to tell you why, and you can disagree with me later, and you will be wrong. So here's me, Head of Engineering Practice at 6 Impossible Things Before Breakfast. You can find me at hatcat01 on all the socials. I'm the chair of BSI IST5, which means I'm the chair of programming languages for the British Standard Institute. This is the mirror group of SC22, and I'm sure you all know what that is. I'm a member of the BSI IST/5/-21, which is the C++ panel. And I'm also now the convener of ISO/IEC/JTC1/SC22/WG21, which the rest of us know as the C++ Standard Committee. I'm also a member of BAFTA because, why not? I'm on the advisory board of a doctoral research group called IGGI, which is Intelligent Games and Gaming Intelligence. Do give it a look. If any of you fancy pursuing doctorates, I think there might still be time for you to get in there. I'm a STEM ambassador. This is a thing that happens in the UK where I go to schools and colleges and say, hey, STEM, science, technology, engineering, mathematics, it's brilliant, go and do that. Do consider outreach to schools. That's how we get more engineers, and we are very short of engineers. And I was a co-founder of #Include. I'm also a husband, father, singer, musician, actor, director, chef, bon vivant, beard wearer, and cartoplect. Would anybody like to guess what a cartoplect is? Sorry? You're very close, but wrong. Okay, you'll find out shortly. I also wrote a book. Who's heard of this book? Now, you see, normally when I say this, I say, and let the record show that more than 80% of the audience raised their hands. But I don't need to crack that joke this time, because apparently it's a set text here, which is gratifying and humbling and very weird. But there we are. I hope you like it. I hope you don't feel forced to read it, and I hope you enjoy it. That wasn't the response I was expecting. Thank you. The rest of you should buy it, though. That's what I'm just saying, Now, get your phones out. So the agenda, the nature of abstraction, C++ features that support abstraction, the art of working at the correct level of abstraction, bad API design, better API design, and bonus content if we have time. Do ask questions along the way. I will stop at each section boundary and check in with you all, make sure you're awake, still breathing, all that sort of thing. You can also ask questions at the end, or we can have the bonus content, or both, depending on when the doors get unlocked. I should point out, this talk is motivated by years and years of talking to graduates before they properly enter the industry. So you might find some of this stuff really, really obvious. But you need to know that it needs teaching, and that it doesn't seem to appear to be present on the typical undergraduate syllabus. Your mileage may vary. I know you've got a great man in Tom Tesh here. He's top fellow. Anyway, let's look at the nature of abstraction first. I'm going to start with a little etymology. So I asked a bunch of folk what they understood by the word abstraction. I didn't ask any large language models. And I got a big pile of rather varied answers. So the Latin root of the word is trahere, which means to drag or pull, and it gives us words like tractor, and it also gives the word subtract, which is literally to pull under, but more meaningfully to take from, as well as retract, to pull back, for example, to retract a statement. We've got contract, which is to drag or draw together, and extract, to draw out, and extract and retract may seem quite similar, and one of the confusions we have is the precise use of these prefixes. And when we come to abstract, which means to draw off from, or to draw away from, we might be grasping for a meaningful understanding of the word. And worse still, the word abstract can be a noun or an adjective or a verb. Yay, English. Looking at nouns, an abstract can be a summary of a longer publication. It can be a theoretical way of looking at things, something that exists only in an idealized form. Used as an adjective, it can mean conceptual or ideal, and it can also mean difficult to understand, which is very defeating. Used as a verb, it means to summarize or extract by means of distillation, or to produce an abstraction. And after writing this presentation, I was left with the notion that to abstract means to form a conceptual summary. That's what we'll focus on here. And if you've read beautiful C++, anyone here actually read it? Did you read The Last Envoi? I talk about abstraction in The Last Envoi. It's what. After I wrote that book, I realized, wow, all of the core guidelines are really about working at the correct level of abstraction, getting abstraction right, which is why I ended up writing this talk. Here's another word, plectere, which is to fold or twist or braid. A simplex is a single-fold triangle, and we have a synonym, monoplex. This is also a synonym, uniplex. Now, duplex means to fold. 2 floors in a building, 2 suites in an apartment, two-way communication, full duplex communication. We've got many-fold for complex, and we have multiplex being multi-complex, so comprising several interleaved parts. Complexity describes the idea of being unable to see the forest for the trees. Okay? Things are interleaved in ways which defy simple or simplex apprehension. The result of all the folding and complication is a new thing in itself. And I hope you can see that there's a relationship between abstraction and complexity, because abstraction seeks to draw away the essence, and complexity seeks to create new things by weaving together old things. Would anyone like to guess what a cartoplex is yet? It's a map folder. I love folding maps. We all have our strange foibles. Maps must be folded correctly, otherwise I lose it entirely. No, we fold it this way. Look, 1, 2, 3, 4, over, there we are. Folded map, bloff, we can use it again. Anyway, we need to cover the closely related concepts of encapsulation and information hiding. Now, these are often used interchangeably with the word abstraction, usually at the cost of clarity. So encapsulation is the process of enclosing one or more things into a single entity, and that entity is called an encapsulation. There's a lot of this around. Is it a verb? Is it a noun? Now, C++ offers a number of encapsulation mechanisms, and the class is the most obvious. Take some data, add some functions, wrap them up in a pair of braces. Put a class, or struct, and an identifier at the front, ideally a good one. We all know naming's hard. There's the enumeration. Take a bunch of constants, wrap them up in a pair of braces. Put enum and an identifier at the front. Function definitions are a form of encapsulation. Take a bunch of instructions, wrap them up in a pair of braces, put an identifier and a pair of parentheses and some parameters outside. How about namespaces? Take a bunch of definitions and declarations, wrap them up in a pair of braces and put namespace and an optional identifier on the outside. Source files work in a similar way. Take a bunch of definitions and declarations, put them in a file, save it to your file system with a meaningful name. Modules, they're our first new encapsulation mechanism in a long time. Take a bow, Gabby. Honestly, this is the man we have to thank for modules, amongst many others. It was a team effort, but... But they work in a similar way to source files. Take a bunch of definitions and declarations, put them in a file, add the export keyword at the top, save it to your file system with a name. Encapsulation is only part of the story, because as anyone with any experience of modules will tell you, there's more. There is more. Because all we've done in each of these examples is gathered things together and named them as a single entity. And if we're smart, we'll have gathered related things together. Now, information hiding is a more subtle activity, and that requires you to make more careful decisions. In addition to gathering, you've got to decide which items you're going to reveal to the outside world and which you're going to hide. Information hiding implies that some encapsulation is taking place. But encapsulation does not imply that information hiding is taking place. Okay? Some of the encapsulation mechanisms of C++ support information hiding. The class gives us access levels. Members within the private implementation are hidden from clients of the struct. And this is how we relieve clients of the burden of enforcing class invariants. Okay? By hiding the implementation, they can't break them. They say, nope, this is what a class, this is how it behaves, these are promises that we make, and you can't muck around with them because all of that stuff is private. The enumeration offers no information hiding. There's no way of exposing only a few members of an enumeration. Functions hide information perfectly by merely exposing an identifier and a return type while hiding away the implementation. Normally, you'll forward declare a function and say, I'm going to define this function later on. Don't worry, promise, it'll be fine. It's all hidden away. Namespaces can expose declarations and hide definitions by distributing over more than one file. You can open a namespace, and then you can open another file, open that namespace. The std namespace, that spreads over many files. So there's a kind of information hiding going on there because you might have declarations in header files and definitions in source files, all within the same namespace. Abstraction, though, is a tricky word, and matters aren't helped by the fact that the result of an abstraction is an abstraction. Shall I step back? Is that high-pitched whine me being in front of the speakers? Am I the only person who can hear the high-pitched whine? Have I got tinnitus? Okay. Sorry, everyone. Yeah. Where were we? Yes, abstraction. The result of an abstraction is an abstraction. The result of an encapsulation is an encapsulation. Abstraction, it's a tricky word. But let's consider the process of abstraction. So in the same way that we just considered the process of encapsulation and information hiding, in a programming context, abstraction means identifying and isolating the important parts of a problem, and then drawing them off and discarding the remainder. Now, what we're doing is we're separating them from the details of the implementation. So we label abstractions with identifiers, and again, consider the nature of functions. We bundle a set of instructions into a single entity, and we label it. The function is an abstraction with a name meaningful to the problem domain. So similarly with classes, the class is an abstraction with a name that's meaningful to the problem domain. It contains relevant functionality to model behavior that is implied by the name, and optimally documented somewhere, because we all write documentation, don't we? But the art of abstraction is deciding what should lie within the scope of the abstraction and what should remain outside. And this is where it differs from mere encapsulation. And I use the word art advisedly, because there's no mechanical method for deciding where to draw the line between what is relevant to the abstraction and what is not. It's entirely up to you. And that ability comes with practice and experience. And you'll have heard me use the phrase problem domain. And before I came to this talk, I assumed there was no controversy about the difference between the two, and I was really quite wrong. Simply typing problem domain versus solution domain into Google was quite enlightening. And this is from a blog called Shah World, which sadly has been inactive since July, about 10 years ago. But I quite like this definition. Problem domain, or problem space, is an engineering term referring to all information that defines the problem and constrains the solution, the constraints being part of the problem. Solution domain defines the abstract environment where the solution is developed. So just get problem and solution sort of in your mind. You've got the two separate domains. He then goes on to say the differences between these two domains are the cause for possible errors when the solution is planted into the problem domain. And he is absolutely not kidding. You know, when you start using the implementation as actually part of your solution to everything, you're not in Kansas anymore, I can tell you. It's a really significant point. So consider the int keyword. Does it live in the problem domain or the solution domain? Now, if you were not on your guard for me asking trick questions, because I sometimes do that, you would probably say it's the solution domain because you write C++ programs which solve problems using the built-in types. But what if the problem is, how do we represent data in RAM or in CPU registers? Now, int is part of the problem domain. The solution domain is a pile of assembly language instructions. Problem domains go on to become solution domains for other problems. And we'll look at this again later on. Actually, let's look at the CPU. How do we get to int? This is what compilers generate code for. And this is a diagram of a CPU, which I found on the Red Hat website. Always good for... There's lots of interesting articles on the Red Hat website. It's a great compiler. The GCC is a great compiler, but Red Hat are great educators as well. Worth bookmarking. I've actually found lots and lots of diagrams of CPUs, each with different contents. I had to find the one that was operating at the correct level of abstraction for this talk. You can start anywhere you like, really. The operation of a CPU is a constant whir of execution and state manipulation. Why isn't that in the center? That annoys me. All right. So you can see the A and B register, which are places where data is stored. And then you have the instruction register, which contains a single instruction. There are two of those. And then you can see the ALU, which combines registers and instructions to produce a result in the accumulator. That's written back into the L1 data cache, or it could be written to the instruction pointer, since the instruction might be to jump, which would update the instruction pointer somewhere else. In which case the registers might contain the current instruction pointer and the relative jump size. The L1 data cache may get written back to the next level data caches. The instruction pointer points to the next instruction to be executed. Round and round it goes. It's very exciting. But this diagram is an abstraction of the silicon, which makes up the CPU. The billions of transistors, the substrate manipulation, all of the really mind-bogglingly tricky stuff that processor manufacturers do inside their foundries can be represented by this diagram. The important features are state and execution. State is inspected and manipulated via execution to yield new state. I don't want to sound like I'm overstating this, but the complexity of a CPU is absolutely tremendous, and increasingly so as the years go by. One thing this diagram actually lacks is the notion of multiple cores, or branch prediction, and instruction look-ahead, and things like that. I found the diagram that was the correct level of abstraction for this talk, and I thought, you know, you can have really busy, complicated things, but you'd lose sight of the meaningful point I'm making, which is it's all state and execution. That's the important stuff. When we look at the history of programming languages, actually, they all involve state and transformation of state. The first language I learned was Atom Basic on an Acorn Atom 46 years ago, back in 1980. Who here is younger than 46? No, actually, no. That would be a distressing quantity of people. Then I moved on to Sinclair Basic on the ZX81, then to Z80 assembly language, 68,000 assembly language, and all of them involve state and execution at different conceptual distances from the CPU. When I first started learning C, I was able to apprehend it as a macro assembly language. I could directly map between assembly instructions and C instructions. So a for loop looked like a conditional jump back to earlier in the code, and a bit shift operation looked exactly like a bit shift operation in 68,000. The distance of abstraction was very, very small. C++, however, offered a different kind of abstraction, and we'll take a look at that next, but I'll take any questions you might have first. I have bludgeoned you all into submission. Okay, great. Well, let's start with the easy stuff. Int is the fundamental built-in type. You may have heard of long or short, but int is the machine word. And it can be modified with unsigned, please don't do that, as well as long and short, as I said earlier. It's representation of data inside the CPU, be it in registers or the cache. When I first started programming CPUs, the registers were integer registers. Particularly on the ZX Spectrum, if you wanted to do any non-integer arithmetic, you had to go to the built-in ROM, and it used the RST28 instruction to launch into a fiercely cunning postfix floating point calculator. And it was a thing of beauty because in something like 4 kilobytes of Z80 instructions, it offered a scientific calculator. And I'm still astonished by that. I can't remember the last time I saw a program written in 4 kilobytes, let alone an entire calculator. I spent the whole of the 80s working with integer maths, and I worked in millimeters. And it seemed precise enough for my purposes. You know, the distance from Reykjavik to Ankara in millimeters can be fully represented in a 32-bit value. And I was never working on those kinds of distances, so yeah, just do everything in millimeters, it's fine. Yeah, well, may you laugh, Gabby. That went wrong. And I first came across floating point with the advent of the 387 coprocessor, which some of you may have heard of. Actually, I'm sure has anyone heard of the 387 coprocessor who's under 40? Oh, right. Well done, Ken. I used to do this thing where I'd say, hands up anyone who was programming in the 2010s, and then the 2000s, and then the 1990s, and then the 1980s. And as time has gone on, I'm the only hand left up. So I'm just embracing aging. It's a thing we should all do. Anyway, the Intel 80386 and the 387 coprocessor would work in parallel, and the cunning programmer would be able to work to much greater precision than fixed-point arithmetic would allow. Interesting, an aside on parallelism there if we have time. Anyone heard of the Intel i486DX? The usual suspects, yeah. This was the first chip with an integrated maths, the first Intel chip with an integrated maths coprocessor. No longer were 2 parts needed. Floating point arithmetic was actually built into the silicon. The i486DX, if you were into PC gaming in the 90s, that was the processor to have. You know, everything was just brilliant from there on in. All of this narrative that I'm sharing here is contained in the type float. Okay? That one-word float tells this huge story about numbers and arithmetic. Floating point maths is quite hard still. Most, I think, of the next few papers I'll be writing for the committee will be trying to set floating point right. It's a big job. When you use the float type, you're simply selecting a separate set of floating point registers that's present in most modern processors. Things start to get a little weird with bool. This is for storing Boolean values. True, false. And it would not be unreasonable to assume that this type is represented by a single bit, but that's not necessarily the case. A quick glance at some output from Compiler Explorer will reveal that it's an integer, an 8-bit type for MSVC and GCC and Clang. It's quite wasteful, but there we are. Where 0 means false and everything else means true. And this might seem like quite a waste of time, but the most efficient implementation requires those extra bits. Implementing as a single bit would introduce more complexity to the generated code. It would diminish performance. There's a trade-off there to be made between size and speed for this abstraction. Char is a strange thing. I've just realized I'm 35 minutes left and I'm really waffling on. Text is difficult. I'm just going to say that. Read about it. Go to it. We have a study group called SG16, which studies Unicode. Man, it's right, void. Okay. And I suppose stood null put a T, which is the type of the null put a literal. So now we've got some abstractions for data in the processor. So what about abstractions for execution? So this is the plain and simple function, and it's easy to tell what it does. It has a meaningful name, which conveys that the parameter is going to be multiplied by itself. Note that the name is clearer than the code, at least marginally. Incredibly, you might say that square is potentially ambiguous as a name, while the code is not. Square could mean multiply a number by itself, or form a square of a particular side length, or it could even be a test to see if a number is square, which returns us to the observation that naming is hard. Identifying your abstraction is the most important part of forming one. Being able to say what its name is, what it identifies. But while the C++ code is unambiguous and immediately apprehensible, the assembly code is not. And there was a time when C was a high-level language, and assembly was a low-level language. And level here means level of abstraction. Programming in C allows programming at a higher level of abstraction than programming in assembly. Programming in C++ allows programming at a still higher level of abstraction. Nowadays, though, very few people write in x86 assembly language. I actually don't know anyone, and I work on the committee, I don't know anyone who actually hand-rolls x86 assembly. Consumer chips are so full of bells and whistles to improve performance that it is an absolute waste of time to go straight to assembly. It's a better idea to let the compiler optimize your code for you. Compiler writers know exactly what they're doing, more so than you could possibly imagine. But full declaration of functions is another form of hiding complexity. By simply stating that the function exists, you're advertising everything that the client needs to know. They don't need to see the implementation. They only need to know that the implementation exists and that it does what the name of the function seems to imply or what the accompanying documentation says it does. And this is not the only form of abstraction available. A new facility in C++, or new since C anyway, is function overloading. This allows you to reuse a function name. It's a form of polymorphism. The name is the important thing. The implementation is unimportant. Okay? Another way of viewing this is that the abstraction is independent of the type. It doesn't matter whether you're trying to square an integer or a floating point type. Square means the same thing. What complexity does this hide? And that's a question we'll come back to time and time again when considering abstractions. What complexity are we hiding? Here, simply, the type of the object being operated on. That's the complexity we're hiding. We're left with a pure name. And we can go still further, of course. So this is a generic function, making explicit that the algorithm is irrelevant to the type, hiding yet more complexity. The use of requires clauses can further refine the declaration to make clear what kinds of type can be passed in. But finally, we have lambda expressions, which construct a closure, an unnamed function object capable of capturing variables in scope. These are functions that can be passed around to functions, again, hiding complexity. This time, the complexity of mucking around with function pointers. Please don't ever use function pointers. Thank you. I said just now that programming in C++ allows programming at a still higher level of abstraction. But consider what that means. The native assembly instructions are replaced with more understandable C instructions. The complexity of assembly language is replaced with the relative simplicity of C instructions. But what about C++? Is that an even higher level language? Here's a house example. Okay, this is a struct, which you can think of as a record in a database table. And in C, a typical interface might look like this. Now, this seems like a rather verbose way of modifying the members of the struct, given that you have a pointer to it in the first place. And I detest trivial getters and setters. I detest them so much that I devoted an entire chapter of hatred and bile in my book to getters and setters. And this is precisely what you can see here. Now, you could always write superior, non-trivial interfaces, but it's also easy to turn this into an untidy API, and you're still exposing the data to client interference. Classes make things a lot easier, especially with some of the additional features of C++. And in a breakaway tradition, I've put the private interface at the top so you can more easily observe what's going on. One thing that C functions allow you to do is to abstract problem domain activity into the solution domain. And I'm foreshadowing here how model view controller methodology can improve the level of abstraction, which we'll look at later. Class polymorphism is not new to C++. It was available in C, but you had to hand-roll your solution, and it would look something like this. You would write code by switching on the has type and calling the appropriate function like this. And all sorts of things could go wrong here. you would have to manually ensure that you covered all cases. You would have to ensure that if a new enumeration was added to house type, then all the places where that enumeration was used would consider it. And this is a terrifically hard problem, requiring extremely disciplined behavior on the part of your engineers. Now, in my experience, engineers can be quite lazy. I think lazy engineers make good engineers, frankly, but that's another. But this was widespread practice, switching behavior on a type field in a struct. But now we have the virtual keyword, and I've restored the public interface to the top of the class declaration, and the virtual keyword signals to the client that the function dispatch may be resolved at runtime. I'm going to skip through this, but the point is, suddenly, your polymorphism is constrained. The complexity that's being hidden is the complexity of choosing behavior based on dynamic type. Okay? And this complexity is not necessarily part of the CPU. It's part of the way that programmers write code. And this is the thing. C just abstracts the CPU instructions. Here we've got an abstraction that's more about how humans work. Static polymorphism is also available to classes, just as it is with functions. And this takes a little more consideration. So polymorphism eliminates implementation detail. It retains the identifier without having to specify certain parts of the abstraction, particularly the types. So dynamic polymorphism hides all the type information behind a virtual function pointer. Static polymorphism hides all the type information behind template parameters. And this is most obvious with the standard library containers. What complexity is this abstraction hiding? It's the complexity of implementing the data structure for a particular type. A class is a set of functions and data with some invariants, and if the data types don't matter, they can become template parameters. In fact, recall the full definition of a vector. The mechanism of defaulting is another abstraction mechanism. What complexity is it hiding? It's hiding the complexity of default behavior. You know, this is not a trivial problem. It's solved for you by default arguments. And there are other abstraction facilities offered by the class and struct furniture. But you get the idea. The class is the primary piece of problem domain abstraction. It enables you to model things from the problem domain in the solution domain. A meaningful name and a credible API are the essence of your abstraction. But to reiterate, structs and classes abstract from the problem domain. Functions and built-in types abstract from the solution domain. Problem domains become solution domains. And this last point is very important, and we'll see an example of it later when we look at the OSI model. So here's an interesting question. Are namespaces an abstraction facility? After all, they take a bunch of declarations, wrap them up in a pair of curly braces, and give them a name. So the effect of declaring something in a namespace means it goes from this to this. But I don't think that's actually hiding any complexity. Namespaces provide a facility to disambiguate common names. That doesn't remove complexity. It makes the code easier to read. It increases the number of useful names you can give to declarations. But it isn't hiding any complexity. If anything, it's preventing complexity. Look at these two function names. You know, it's quite usual to name abstractions by domain and then by abstraction so that you know whereabouts the things live and what they're for. And this is fine while your code base is reasonably small, but once you reach 1 million lines of code, which is not uncommon at all in game dev. The total code base when I left was in excess of 10 million lines of code. But you're in danger of naming things like this, which becomes pointless if you're writing code inside the AI entity code modules. Nothing is served by making your names long and prefixing them with AI _ entity. The facility of namespaces allows you to offer domains of abstraction to the compiler and a simpler means of disambiguation. It does bring its own problems. So this is a using directive, and the core guidelines suggest you should avoid declaring a using directive in a header file. There is an exception, actually, which is the std literals namespace. You need this to use string literals in header files, but I don't think the core guidelines goes far enough. I think that with the exception of the std literals namespace, you should never use a using directive. Again, I devote a whole chapter of my book to why you shouldn't do this. which you can go and read. Libraries, on the other hand, are most definitely an abstraction facility. In tandem with header files, they're the bread and butter of code reuse ever since C was a twinkle in Kernighan and Ritchie's eyes. It's a simple mechanism. So what's going on here is that the compiler parses the declarations in mystuff.h and uses that to inform the remainder of the translation unit. And this is great. You've got a consistent way of making a set of declarations and reusing them in other translation units. You're able to adhere to one definition rule and have that one definition be consistent. This is brilliant. The definitions of those declarations are either made in the header file with static linkage or included in a library file. And there we are. mystuff.lib abstracts all the implementation complexity behind a simple header file. That's quite some feat. And we've been using this mechanism for a long time now. It's not without its costs, which leads us to the question of what is a zero-cost abstraction. And I'll answer that after we cover modules, which is the first new language-level abstraction facility for a long time. So consider the inclusion model. And the problem it solves is ensuring identical redeclaration of types and functions by means of lexical substitution. So when you type #include matrix.h, for example, the preprocessor will hunt around for that file, open it, add it to the stream of text for compilation. And it comes with a few problems. The mechanism used by the preprocessor to find the file is implementation defined. What works on one toolset may not work on another. The preprocessor is language agnostic. It knows nothing about whether or not the code is correct during inclusion, potentially burning up valuable time before the compiler gets to it and tells you that it's malformed. It relies on the linker to provide the definitions for these declarations, which again knows nothing about compilation. The inclusion model attempts to solve the problem of code reuse without using the compiler at all. And this means that opportunities for optimization are lost. We can and must do better. Enter modules. The big deal with modules is that they turn libraries and programs into reusable components. A module is a set of source code files that are compiled independently of the translation units that import them. They have no effect on the compilation of the translation unit that imports the module. After a module is compiled once, the results are stored in a binary file that describes all the exported types, functions, function templates, and class templates, and the compiler can process that file much faster than a header file. And the compiler can reuse it every place where the module is imported in a project. This is a fantastically hard thing to say with the inventor of modules sitting in front of me. I really hope I got that right. But the big deal with proposing modules came with a big pile of problems to solve. What do you do about preprocessor symbols? Argument-dependent lookup, which is a hilarious problem. And it took a long time to answer those questions. This isn't a primer on modules. Do read up on them. Daniela Engert does some great talks at CPPCon, Meeting C++ on modules. There's a lot to them. It's absolutely worth getting the hang of modules. Where are we? Right. So from the top, the first line informs us that we're declaring a module. I took this from cppreference.com. The second line imports IOStream. Note that it doesn't include it. It imports it. And when the compiler imports IOStream, it will see that it's not a module, since it doesn't contain an export keyword. The third line actually defines something, a function called hello, and marks it for export into the module defined by the source file. Now let's look at a source file which consumes this module. So I hope this is reasonably obvious. At line 1, rather than include hello world, we import hello world. Otherwise, things don't look too different from the familiar include model. The source file is importing a definition, a void function called hello, and calling it. Now, I'm not an implementer. Those folk are amazing, and I just write games. But I would like to think that my mental model of the inclusion process is not too far from the import process. I imagine that when I hit build in my IDE, the dependency scanner will look at the modules, build them first if necessary, and then simply add them to the compilation stream, as requested by the import declaration. If you're familiar with precompiled headers, you may see parallels here, but modules are not precompiled headers. Modules can selectively export names. Precompiled headers just export everything. They happen in the preprocessor. They are dumb in that regard. Looking back at the import of IOStream, so when hello-world.cpp is compiled and turned not into an object file, but a module, it will include all the types, functions, and templates that are declared in that file. And it only needs to be parsed and built once, rather than every time, as is the case with headers. This alone justifies the use of modules for me. What complexity is this hiding? It's the obvious question, but particularly where we were using the preprocessor and the linker to enable the reusing of code with all the problems that brings, we're now doing it within the compiler itself with much finer grained control available. We've migrated from encapsulation to abstraction by offering the encapsulation in place and offering control in the solution domain. And you might think that this means the end of the linker, or at the very least the librarian, but there are some considerations. For example, with Microsoft's compiler, a module and the code that consumes it must be compiled with the same compiler options. And also, if you want to consume the C++ standard library as modules, you must compile your program with these two, which is standard stack unwinding and the DLL version of the standard library. Is that still the case? Yes. I didn't want to put you on the spot there, Gabby. Microsoft are a very fine company. They build MSVC. It's a good compiler, and all game devs will probably still be using it for years to come. Stack unwinding is an expensive feature to add to your program, and not one that I'm inclined to use in game development. Well, that's that section. Any questions? Do I keep going? Do I keep going? Right. Anybody know what this is? Wow. Get you. All right. Yes. Yes, it is. Do you know why I like writing games? Nobody dies. If I release a game and there's a bug in the code, the worst that happens is the game will misbehave or crash. And users will get grumpy, and they'll flame the notice boards, or if they are sensible and have a sense of proportion, they will simply restart the game. Okay? Games are not medical imaging equipment. Okay? Imagine that going wrong. It's not a tidal barrier controller. Yeah. It's not a nuclear reactor. You know, it's just a game. This is a nuclear reactor. Actually, it's not a nuclear reactor. It's the control room for a nuclear reactor. It is indeed the control room for Chernobyl Unit 3. When it comes to complexity, a nuclear reactor is hard to beat. I don't know how to operate a nuclear reactor. There are many kinds of reactor, but until we can solve fusion, they all work on the principle of nuclear fission, releasing vast amounts of energy per atom. The control room is staffed by several technicians with different sets of expertise who monitor a particular part of the system. Those technicians gather information, make decisions, and then respond to that information. They are rather like state machines in that regard. They gather information from all of the feedback devices scattered about the control room. Some of those devices are little needles that rotate from left to right. Like the volume, something decreases, like the volume of fuel. They may be numeric displays or 270-degree displays. There are all sorts of ways of presenting information, but the point is that they are all presenting information. I remember when I was a child, I used to look at my grandfather's barometer, and it had two needles, rather like this one. The dark needle would show the air pressure, and the brass needle would be used to record the air pressure at a moment in time. And every morning, as my grandfather went to work, he'd tap the barometer and say, down by 12, going to be windy, or whatever was appropriate. And then he'd move the brass needle. And one day I asked him, could you control the air pressure with the needle? I was 6, come on. He laughed and said he wished it was so, that he wouldn't have to go to work ever again. Now, back in our nuclear reactor control room, if the technicians want to reduce the output of the nuclear reactor, they would turn the knob on the left anti-clockwise. No, of course they wouldn't. This is an air conditioning control unit, not a nuclear. Yeah, none of you laughed. You were all like, yeah, this is a nuclear reactor. The finest engineering minds in Belgium are gathered before me. But the display doesn't change at all. All that changes is the position of the knob under human activity and the operation of the air conditioning unit. This is a description of human activity that scales well. It's how we interface with machines. We collect input. We decide on changes, and then we enact on those changes. and be it an air conditioning system controlled by someone in a warm room, or a nuclear reactor control room controlled by 10 technicians, or a healthcare system controlled by tens of thousands, as we have in the UK. The process is collect information, decide, enact. And I know I'm labouring this point, but do bear with me, because we're now going to talk about my most hated API decision after I've taken any questions. Short one there, because we're running short on time. Let's talk about this piece of code. So this is an example of using trivial getters and setters, and they simply reach into the implementation of the class and return or modify the value. On the surface, there are some things to commend in this approach. You can search your code base for getX and setX and to see where the code changes. And it's easy to set a breakpoint in the function so that you can trap every instance of where users retrieve the value or modify it. And it honors the idea of keeping data private. The data is encapsulated behind an API. But there is a core guideline, C.131, avoid trivial getters and setters, which advises against this approach. And they are trivial functions which simply put a roadblock in the way of direct access to X. I want you to look at this picture. There we are. Is this barrier at all effective? It's not. It is not. Not unless you're trying to prevent people who don't like driving on the grass from getting past. There it is effective. That is a very, very small set of people, I can assure you. And this is a great metaphor for get-set functions. And I want to take you back to the days of C. Without access specification, all data is available to everything. Significantly, it was usual for data that was not in the scope of the currently executing function to be directly available for modification. And typically, you would see something like this. Now, if the engineer was lucky enough to be the only person expected to modify such data, they would be able to reason about it with a valuable degree of certainty. They knew where the data was modified, and they knew where the data was read, and they would therefore be able to identify bugs related to the data. Sadly, as teams grew bigger and individual pieces of data became more important, keeping hold of responsibility for them became harder. The data would be declared in a header file, making it accessible to many engineers. Reasoning about the data would become a lost cause. Coding guidelines would be written about the data. Arguments would break out in the kitchen about who was mucking about with it. Meetings would be called to set policy once and for all about who was allowed to write to the data and under what circumstances. Documentation would be added to the declaration. Everyone would hope it was being kept up to date. Everybody would hope the person who was keeping it up to date wasn't them. Everyone would hope that all the other engineers were reasoning about the data in the same way. Everyone would hope 6 months later that all the other engineers were continuing to reason about the data in the same way. The important thing to remember is that once data is declared in a header file as an external declaration, not only is all control lost, but all hope of control is also lost. And whatever you think you might mean by this piece of data, Hiram's law applies. Who's heard of Hiram's law? Good. Hiram's law, with a sufficient number of users of an API, it does not matter what you promise in the contract. All observable behaviors of your system will be depended on by somebody. You no longer own the data, and yet you remain responsible for it. Searching the codebase for an identifier with a useful and therefore common name becomes a nightmare of context assessment. Eventually, a bright engineer would hide away the piece of data behind a pair of functions, one to write to the data and one to read from the data, and it would not make reasoning about the data any easier, but a search through the codebase for the call sites of those functions, along with the breakpoint of those functions, would combine to reveal under what circumstances the data was being changed. If they were really clever, they would find a way of naming the functions to reflect what their purpose was in the problem domain, in an attempt at producing self-documenting code. Who's heard of self-documenting code? Mythical unicorn. No, this is not the code you're looking for. It's a lie. It's a lie. It doesn't exist. Don't believe it exists. Here's an example. If the piece of data was an elevation above sea level, they might name the function like this. Now, this wouldn't prevent people from arbitrarily changing heights at inopportune moments throughout the code base, but at least it would signal what they were doing and perhaps improve client readability by using nouns for functions that queried values and verbs for functions that modified values. Gatekeeping the data in this way allows you to search for it, and you get the added bonus of being able to set breakpoints in your debugger so that you can keep a careful watch over it. Then along came C with classes, with access levels, with member functions, access levels. Finally, the data belongs to me. I can make it mine by declaring it private. Nobody can touch it except through one of the public member functions, member functions. So in C, it was possible to store pointers to arbitrary functions in structs, but member functions with an implicit instance pointer, this, as the first function parameter, were a leap in usability. The world was a brighter and shinier place. And the programming style of hiding your data behind a pair of functions was no longer simply a bright idea. It became normal practice, enforceable by the language itself. New advice was offered, loud and clear: make all your data members private. Who said that? Make all your data private. This is what we just teach, isn't it? It's only half of the situation, though. A new keyword was added, class, to distinguish from struct. So for backward compatibility, members of structs remained public by default, while members of classes were private by default, reinforcing the idea that data should be private. And with the ability to keep data in a private interface came the opportunity to prevent, trivially, people from interfering with that data. You could create an object, you could provide getSet functions to get at the data, and that, in a nutshell, is encapsulation, not abstraction. Encapsulation is one of the core principles of object-oriented programming, restricting access to the object's parts and combining data with the functions that operate on that data. It's a safety feature that easily improves the ability of the engineer and the users of the encapsulation to reason about what is going on. And suddenly, encapsulation was available to C engineers, and this sort of thing happened. It saddens me enormously. What is the actual difference between this and a struct of the public data semantically? There is none. All you're doing is erecting extra barriers to the same thing that don't really serve much use. You're driving around the barrier. The question you need to ask is why you care about people modifying the data. Does arbitrary tweaking of member data invalidate instances of your class? Is there some restriction on your data? And if so, then your setter function needs to do a little work. For example, the floor area should not exceed the area of the plot. So now this setter function is no longer trivial. It has a reason to exist. So the condition that the floor area cannot exceed the size of the plot is known as a class invariant. And more generally, a class invariant is a condition that must hold for all valid instances of a class. Access levels allow a class designer to easily preserve class invariants by checking the effect of operations on the member data and ensuring that all the data retains valid values. This guideline gives as its reason, a trivial getter or setter adds no semantic value. The data item could just as well be public. And as we can see from the house example, that's exactly the case. There's no semantic difference between struct house and class house. The member functions are redundant. There's an operational difference, because you can set breakpoints and stuff like that, but that has no impact on the semantic nature of the house abstraction. When creating a class and designing its interface, it's quite usual to think of aspects of the abstraction being modeled with numbers, because this is a computer you're writing for, after all. The temptation becomes simply to make those aspects numerical data members. If a client wants to change something, they call the function to set the new value. And after some checking to maintain class invariance, the corresponding data member is modified appropriately. A class is not an empty vessel for pouring data into. It's to be used as an abstraction of the problem domain into the solution domain. And if there's one thing I want you to take away from that talk, this is it. It's an abstraction of the problem domain into the solution domain. Right, any questions before I move on to the next section? 5.5 minutes. I might overrun a little. I'll try not to. Better ABI design. So this is kind of rather missing the point of good class design. A class is an abstraction of an idea. It's not a bundle of data. The reason why change height and height are good function identifiers is because they convey in English what is going on. The client engineer doesn't care that they're changing an int by some amount. They care that they're changing the height of the object. They don't want to know the value of the height member. They want to know the height of the object. These two things operate at different levels of abstraction, and leaking abstraction details is bad practice, unnecessarily increasing the cognitive load of the client engineer. Okay, go back to the introduction. My suggestion was that everything works by collecting information, making a decision, and then acting on that decision. In this piece of source, you can see that the client engineer is going to call the height function, make a decision, and then call the change height function. And we know what these parts of speech are, and we should use this information to improve the quality of our conversation with our engineer. This is the important part. Change height is a verb. Height is a noun. And when you look at it in those terms, suddenly the ideal API becomes a lot more apparent. Do you think this is any better? How about this? We can see there are two things you want to do with an elevation. You want to change it or set it. But Guy, I hear you say, that's a setter function. And it is, but only because I couldn't think of a better name than set elevation. The semantic is not diminished. The elevation just happens to be implemented in terms of a number. So it looks like I'm directly writing to the data. And my inability to think of a better name makes me wonder if I have the right abstraction here. Am I losing clarity by having to use a name as generic as set or change? Is there a better abstraction, something which hides complexity, waiting to be found, that explains things in clearer English? The trick here is to think in terms of nouns and verbs. Code becomes much more legible if you have single words describing what you're doing to what things. Underscores make reading harder. Now, what do we really mean by modeling? Who knows what this is? You'll need to be a jazz fiend. We don't have any jazz fiends in the house. How very disappointing. They're all dying off, aren't they? Okay. There's a great jazz album called Survivor's Suite by Keith Jarrett. It was recorded in April 1976. That's the original cover. So here they are side by side. What's the difference between the two? There are things like the photo quality, lighting, absence of text, placement of the chairs, shape of the pool ladder, the pitch of the roof. But when I first saw the Lego model, I immediately thought of the original album cover. There was no hesitation. I thought, oh, that's clever, you know. And the important thing with modeling is that you're constructing an approximation of the original using the relevant parts salient to the problem at hand. When we create a class to abstract something like a house, the chances are that the relevant parts are as described earlier. How much land, how much floor space, how many stories, how many rooms and windows. And this is fine if you're an urban planner. What if you're an architect? You know, important information includes the volume of materials required, the nature of the materials themselves, what the walls and roof are made of, how deep the foundations go. The point about modeling is that it's a relevant approximation in less detail than the original, captured in terms of numbers. And recall class invariants from the getters and setters part. Those invariants constrain the values of the parts of the model. A door to the house, for example, might only open up to 90 degrees, but a window shutter might open to 180 degrees. So there may be a door or window class, instances of which contribute to the house class, describing those constraints. Checking the invariants under modification. And if there are class invariants, then the model needs to be private. And this implies a public interface to control and view the model. And this is the essence of the model view controller paradigm. Oh, I have 1 minute left. Let's not. Oh, no, I think we can. Right. The class is neatly divided into three parts: the model interface, the view interface, and the controller interface. And along with that, what I call the life cycle functions of construction, destruction, and assignment. And I use this approach to my classes wherever possible because it speaks to the client, telling them how to use the object. And you can use this approach to describe the nuclear reactor control room. The reactor core is the model, the gauges are the view, the knobs are the control. And there we have it. 26 seconds. We looked at the nature of abstraction, the etymology, the confusion with data hiding and encapsulation, and we clarified problem domain against solution domain. And then we examined the way that C++ supports abstraction, Next, we looked at some examples of how abstraction is put into practice in the hope of divining how to cement the idea of working at the correct level of abstraction. We looked at some bad API design, getters and setters, and the abuse of classes. And finally, we looked at API design as the hiding of complexity through model view controller programming and the correct use of classes. Any questions? Yes! Yes! You're not getting the bonus content unless you ask Tom nicely. I did. I didn't think I was going to do that. I was waffling on so much at the front. Anyway.
Maybe time for one question?
Okay.
So I have one question about...
Just one. Excellent.
Yes. With reflection, annotations, and const-evaluated exceptions, how do you see APIs going forward? Will they be even more abstract, more maintainable?
Just one question. Yeah, that's...
Very small question, yeah.
Very small question. Yes, 17. No. Yeah, we do keep adding stuff to the standard. People have great ideas and make the language better. But API design, it's all about communicating with the user. Reflection is much more likely to be an implementation detail. It's not going to be part of API design. Exception handling, we're finding new things out about exception handling. If you listen to Khalil Estelle's talks about his exception handling on embedded systems, I found that quite revelatory. So I think we have to continually look at all the features that are being observed and offered, that are being offered and exposed, and use them properly. I train people. I'm still going to be training people not until I die, but certainly for the next decade, because we're always finding new and better ways to use the language. Features don't drive complexity in the language. Most of what we do with the standard is to try and make it simpler. It might not seem simpler, but that's because you're probably confusing familiarity with simplicity. When range-based for loops came in, everybody went, "Oh, come on! This is illegible. This means nothing at all." But we're all now used to range-based for loops. In fact, we should probably all be not using range-based for loops at all, but using the algorithms in ranges and things like that. I've not answered your question. Good trick, huh? Or have I? I have. Oh, thank you. Thank you.
Thank you, Guy, for...